In the United States, in the Arizona desert, there is a lizard that only eats twice a year. Yes, just twice. No more than 2 times, and that's in the whole year. It can go 8, 10, or even 12 months without eating anything, without losing muscle, without getting sick, and almost without aging. But when it finds food, it gorges itself. But when it doesn't find any, it simply waits and lives for 30 years doing just that. The name of this animal is the Gila monster, and it is venomous to humans and has skin like a string of beads, orange and black. Until recently, in fact, until very recently, nobody cared about it in the slightest. And that's how it was until, in the 1990s, a doctor from the Bronx asked a question that seemed completely absurd. The question was, if this animal goes months without eating and its blood sugar remains stable, no diabetes, no crashes, no problems, what does it have in its body that we don't have in ours? And it turns out that the answer to that question is inside you right now. In fact, that's not all. The answer to that question is the reason why your neighbor has lost 15 kilos this year without going hungry. And it's also the reason why, right now, there are clinical trials underway to slow down Alzheimer's, with a molecule that literally comes from the saliva of this lizard. As you can clearly see, it is also the primary reason why many cardiologists are increasingly beginning to prescribe this specific drug to patients who do not currently suffer from diabetes, specifically because of the way it effectively protects their hearts. And finally, it is also the primary reason why you are probably not aging quite as gracefully, or as well as you potentially could be. And here, look at me, what I'm going to tell you in the next few minutes, you won't find anywhere else. Don't like this. You won't find it anywhere, because everyone talking about Ozempic does so as if it were a miracle pill for weight loss. And Ozempic is not that. Ozempic is something very different. In fact, it's something much more interesting and much more important for you, whether or not you have a few extra kilos. What's more, today we're going to look at it from a perspective that changes everything: biophysics. Because when you understand Ozempic from the perspective of physics, what happens inside your cells, and not just from the chemistry, the story you've been told until now seems small. Up to now, that story falls short. If this is the kind of content you're looking for, because this is what I do here for you. But before we go on, I have to tell you something, and it's something that changes how you're going to understand everything else. You can't talk about Ozempic without first talking about GLP-1. And you should know that GLP-1 is not just a simple drug. In reality, GLP-1 is a naturally occurring hormone, a vital hormone that your own body produces. And right now, at this very moment, as you listen to me, the specialized cells inside your intestine are actively making it. That is the power of GLP-1. And you've been doing it since you were born. And before you were born, your ancestors did it, and before them, theirs, and so on, for millions of years. This is one of the oldest signals your body has. The problem is that this signal doesn't last long. Your intestine releases GLP-1, it travels through your bloodstream, does its job, and within a few minutes, your body deactivates it. It's a fleeting hormone. It appears, sends its message, and then fades away. So then, what is Ozempic? Ozempic is a smart copy of this very hormone. In other words, a synthetic version designed in a laboratory that mimics the GLP-1 signal exactly, but with a little trick. It's built in such a way that your body can't turn it off so quickly. Where your natural hormone lasts minutes, Ozempic lasts days. And that's it. That's what Ozempic is. An imitation of something you already have, made to last longer. And that's why, if you don't first understand what GLP-1 is, you can't understand what Ozempic is doing in the bodies of millions of people right now. So let me tell you, what exactly is GLP-1? It is one of the oldest, smartest, and most misunderstood molecules found inside your body. To begin with, I'm going to take you to the laboratory where it was discovered. You will meet the scientists and understand step by step what this hormone does in your brain, in your heart, in your blood vessels, and in your intestine. And I'm also going to show you real research papers, actual studies with names and surnames. And when you reach the end of this video, you will have something you don't have right now. Judgment. Judgment to decide with a clear mind what to do with this information. Whether Ozempic has anything to do with you, if there are natural ways to activate the same system, or if what you're doing with your body is heading in the right direction or not. But before getting to you, before talking about your body, the first thing I'm going to do is take you back to the year 1990 and bring you to a hospital in the Bronx, New York. And once there, introduce you to a man who spent his own salary to buy lizard saliva. And you might ask me why. Well, it's very simple, because no one at his company wanted to pay for it. The purchase of that saliva. We're in the Bronx at the Veterans Affairs Medical Center, a public hospital for war veterans. And it's not Harvard, it's not MIT, it's not one of those brilliant laboratories you see in documentaries. It's a municipal hospital with walls that need painting and budgets that never arrive. And there works an endocrinologist named John Eng. John Eng is a calm man, the son of Chinese immigrants who studied medicine and specialized in hormones. And instead of seeking a position at a prestigious university, he chose to stay at this Bronx hospital, caring for diabetic veterans. They were his people. That was it, what he understood as his best work. But John Eng had an obsession, just one. He had spent years reading old papers that almost no one looked at anymore, about rare animals. And he eventually found a specific vintage model from the decade of the 1980s that had vividly stuck in his mind for years. The scientific research paper talked about the fascinating Gila monster and mentioned, almost as if it were a minor incidental detail, something truly curious. This unique lizard has a strangely large pancreas for its physical size, and whenever it eats a meal, it regulates its own blood sugar levels in a highly specific way that no other known animal does. It was something like that. No one had paid any attention to it, and no one thought it was important. But to a man like John Eng, it truly meant absolutely everything, because Eng knew something vital that many others simply weren't connecting at the time. When we consider an animal that only eats twice a year, yet possesses a significantly hypertrophied pancreas and maintains perfect glycemic control, it is clear this is no coincidence. Such a precise physiological state is a direct result of millions of years of evolution. And that means the lizard must possess some specialized biological mechanism within its body, perhaps some unique molecule or a specific hormone, that ultimately allows it to do what it does. And if that molecule exists in the lizard, maybe it turns out that a similar version exists in us too. Or maybe we can copy the lizard's version and, along the way, cure millions of diabetics. And what did Eng do? He presented his idea, requested funding from the NIH, which is the United States Public Health Organization, and it's the one that distributes money for research. And what happened? They denied his request. They replied that his idea was exotic, speculative, and with no clinical future, of course. They told him something like, "We're talking about the Gila monster here, not a serious animal model. Look, ask us for something else, and when you have something more reasonable, come back." And this is exactly the point where the narrative takes a truly fascinating turn, because a man named John Eng simply refused to throw in the towel or give up on his mission. He did something that almost no scientist does, something that, in fact, goes against all the rules of how biomedical research works. He decided to pay the expenses. He, out of his own pocket, from his salary as a doctor at a public hospital. He bought Gila monster saliva, he bought the reagents. He set up the experiment in his Bronx laboratory with what he had on hand and began to isolate molecules, one by one, searching for what was in that poisonous saliva that could explain the miracle of the pancreas. And he found it. In 1992, John Eng published the discovery of a new molecule, a peptide. He called it exendin 4. And now, wait, because I have to stop you here. Hold on a moment, because the word peptide is going to come up many times in this video, and I need you to be clear about what it means. A peptide is simply a short chain of amino acids. And what are amino acids? Well, they're the building blocks with which the proteins in your body are built. If you put together many blocks, you get a large protein. If you put together just a few, you get a peptide. Small, agile, easy to make, and easy to travel through the bloodstream. Peptides are the most versatile chemical messengers in biology, and exendin 4 is one of them. What was extraordinary about exendin 4? It wasn't just that it existed, it was what it did. ENG discovered that this molecule, this short chain of amino acids from the saliva of a desert lizard, was very similar to a human hormone he already knew, a hormone that your body, mine, and his produce every time we eat. That hormone was GLP-1. The lizard's exendin was practically a plant-based GLP-1, animal-based, but with a decisive difference. While human GLP-1 is deactivated within minutes, the lizard's exendin 4 remained in the blood much longer. It was a more stable, longer-lasting, and more potent version of the same message. Nature, in the body of this lizard, had done what pharmaceutical laboratories would do years later: a version resistant to degradation. Jonek patented the molecule, and he patented it personally because his hospital did not want to cover the cost of the patent. And years later, that patent would become the first drug in the family. It was called exenatide, and in 2005 it became the first GLP-1 receptor agonist approved by the FDA to treat type 2 diabetes. 15 years since Eng spent his salary on lizard saliva, until that very molecule began saving lives in hospitals all over the world. And today, John Eng remains a relatively unknown man. He does not have a Nobel Prize. He also doesn't have an institute named after him, and the pharmaceutical industry has made tens of billions of dollars from the pharmaceutical descendants of his discovery. And he remains a quiet endocrinologist whom almost no one recognizes on the street. But without John Eng, Ozempic wouldn't exist. Without John Eng, Mounjaro wouldn't exist. Without John Eng, this entire revolution wouldn't be happening. And without John Eng, you wouldn't be watching this video. And now you'll see. I've told you the story of the lizard and the doctor who paid for the saliva out of his own pocket, but you're missing a piece of the puzzle. Because exendin 4 imitated human GLP-1, yes, but who discovered human GLP-1? Where did that hormone come from? The one we've been producing for millions of years and that no one had noticed until just a few days ago. For that, now we have to go back another decade, leave the Bronx, and head to Boston at the end of the 1970s. To a laboratory where two scientists are about to stumble, without even looking for it, upon one of the most important hormones discovered in the last 50 years. Now we're at Massachusetts General Hospital, one of Harvard University's teaching hospitals. It was a laboratory that wasn't looking to discover anything about GLP-1, because GLP-1 didn't even exist as a concept yet. And there worked an endocrinologist named Joel Habener. Habener was the opposite of Jonan. He was at an elite institution, had funding, a team, and recognition. And he was obsessed with a hormone that was already perfectly well known at the time, glucagon. And I imagine that this name, glucagon, you've probably heard it before, but let me pause for a moment because it's something that's important to be clear about. In this video, you'll see. If insulin is the hormone that lowers blood sugar, glucagon is the one that raises it. It's as simple as that. Both hormones work together like two hands gripping the same steering wheel. When you eat and your blood sugar rises, insulin is released to store it. When you've gone hours without eating and your blood sugar drops, glucagon is released to free up reserves. Insulin and glucagon lowering and raising. That pair is what keeps your glucose stable hour after hour, day after day, and so on throughout your life. Well, Habener wanted to understand, where did glucagon come from? He wanted to find the gene that produces it. And at the end of the 70s, together with his team, he succeeded. They isolated the glucagon gene, sequenced it, and understood it. But in doing so, they got a huge surprise. Because when you look at the glucagon gene, in detail, you discover that it doesn't just code. It doesn't just code for glucagon, it codes for a much larger protein called proglucagon, and this large protein, depending on the tissue in the body where it's produced, is cut into different pieces. I'm going to explain this with an example because it's important and could be confusing. Imagine a large sheet of paper with instructions written on it. That sheet is the proglucagon gene. If that sheet is read by a pancreatic cell, the cell takes a pair of scissors, cuts out the part that says glucagon, activates it, and releases glucagon into the blood. But if that same sheet is read by an intestinal cell, the scissors cut in different places, all from the same sheet. Different pieces come out, pieces that are not glucagon, pieces that no one had studied before, pieces that no one knew what they did. And that was what Habener and his team discovered in the early 80s. The same sheet, read by different cells, produces different messengers. And two of those messengers, which appeared when the sheet was read by an intestinal cell, were given rather unglamorous names: glucagon-like peptide 1 and glucagon-like peptide 2. That is, glucagon-like peptide number 1 and glucagon-like peptide number 2. GLP-1 and GLP-2. I don't know if you've noticed, but I've just introduced you to the protagonist of our story. Newborn, discovered by some scientists who didn't know what it was for, what it was used for, and hidden in a gene where they were actually looking for something else. And this is where the second important character of our video today comes in, because in the early 80s, a young Canadian freshly graduated with a doctorate named Daniel Drucker arrived at Habener's lab. He was brilliant, ambitious, and became fascinated with those orphan peptides that nobody knew what they did. He decided to dedicate his entire career to them. And at first, this presented a significant and frustrating challenge for him, because when they began the meticulous process of investigating GLP-1 in its original form, which was freshly cut from proglucagon, it turned out that it was found to be almost entirely ineffective in its biological function. They injected it into animals and not much happened. Drucker was risking the early years of his scientific career on a molecule that didn't work. And it stayed that way until one day they discovered something critical. The molecule, as it was initially cut from proglucagon, was not the active form. And here I need to explain to you what that means, because the concept of the active form is going to come up many times in what follows. You see, molecules in the body don't work just by existing. They only function when they have the exact shape that allows them to fit into their place. It's like a key. A key can be made, it can have the general correct shape, but if the teeth of the key aren't properly filed, it won't open the lock. It's a key that doesn't work, it's inactive. Well, in biology, it's the same thing. Many hormones, many peptides, many enzymes are first produced in a preliminary version, an unfinished version, and then the body has to trim them, fold them, or modify them so that they take on their final shape. That's what makes them functional. That final shape is what we call the active form. In other words, the version that fits. The version that already sends signals and the version that actually does things. The rest, the intermediate versions, are inert molecules. They exist, yes, but they don't communicate. Well then, what Habener and Drucker discovered was exactly that. The GLP-1 that was initially cut from proglucagon was an inert version, a key with burrs that wouldn't fit into any lock, and understandably, it didn't give them any results. What was happening was the following. When the intestinal cell took the proglucagon, that big instruction sheet I mentioned earlier, it would cut it into pieces. One of those pieces was GLP-1, but that freshly cut GLP-1 still wasn't useful yet. It had some amino acids hanging off the beginning like a sort of loose end, and as long as that end was there, the molecule couldn't do its job. It was like a key with an extra bit of metal next to the teeth, and no matter how much they tried to fit it into the lock, it wouldn't turn. But it turned out that the cell itself, thankfully, the intestinal cell, had a second enzyme, a second pair of scissors that was responsible for cutting off that extra end. It removed those initial amino acids, trimmed off the excess, and as soon as that second cut happened, the peptide changed. It went from being a key with burrs to a perfectly polished key. It went from being an inert molecule to an active molecule and finally began to do things in the body. That was what Habener and Drucker took time to discover, that GLP-1 was not a single molecule, but two versions of the same one inactive, freshly cut from proglucagon, and another active, ready to work. After the second cut was completed, and only when they finally started working with the correct active form of the substance, the scientific experiments began to yield significant results. And those initial results very quickly started to become truly spectacular and groundbreaking. Once Drucker and Habener finally managed to isolate the specific active form, absolutely everything in the field changed forever. They injected that molecule into animals and began to observe things that had been unimaginable until then. The pancreas, in response to active GLP-1, released insulin. But not just in any way. It released it exactly when there was glucose in the blood, and it stopped releasing it when there wasn't any. In other words, GLP-1 told the pancreas, produce insulin, but only if it's needed and never too much. And this was huge. And let me explain why. Until then, treatments for diabetes worked in a relatively crude way. You see, the problem for a diabetic person is that their body doesn't produce. Either there isn't enough insulin or the body doesn't use it properly, and that's why blood sugar rises too much. The classic solution was to inject insulin from the outside. You inject insulin, their blood sugar drops, and problem solved. But that solution had a serious flaw. With injected insulin, the diabetic doesn't know what's happening inside the patient's body. And once it enters the bloodstream, it will lower blood sugar whether or not there is food in the body. If you inject insulin and then don't eat enough, or if you exercise more than expected, that insulin keeps working. And what happens then? Blood sugar drops below normal, and that's called hypoglycemia, low blood sugar. And it's no joke. Cold sweats, trembling, confusion, dizziness. If it drops too low, loss of consciousness. And if it drops even further, death. Hypoglycemia kills diabetics every year all over the world. It's one of the biggest fears for anyone living with this disease. And this is exactly where GLP-1 first entered the scene, performing a function that was entirely and fundamentally different. Instead of the usual process, GLP-1 didn't simply tell the pancreas, "You need to release insulin right now." It told it something much more specific: release insulin only if there's sugar to lower. In other words, GLP-1 activated insulin only when there was glucose in the blood. If there was no glucose, it didn't activate anything. The insulin-producing machinery stayed on pause, waiting. Imagine the difference. Think of injected insulin as being just like a kitchen faucet that you turn on, and that is it. The stream of water just keeps on flowing out until you decide to manually turn it back off again. GLP-1 is like a smart faucet with a sensor that only lets water out if it detects there's a glass underneath. If there's no glass, nothing comes out. There's no waste, no overflow, no danger. And that's what Haberner and Drucker discovered. Imagine a sophisticated hormone that intelligently and precisely regulates blood sugar levels based on the body's real fluctuating needs at any given moment. This is a hormone that, by its very inherent biological design, is practically and fundamentally incapable of causing the dangerous state of hypoglycemia. And for the entire global world of diabetes management, that was something once considered to be straight out of the realms of science fiction. But GLP didn't stop there. It did even more. It told the stomach to empty more slowly so that food would reach the intestine gradually without spikes. It told the brain, specifically the hypothalamus, to stop feeling hungry. And it also told the pancreas to produce less glucagon so that sugar reserves wouldn't be released all at once. Insulin when it's needed. Less glucagon when it's not needed. A slower stomach, a satisfied brain. 4 different actions and just one molecule, and all of them working at the same time as a team every time you eat. And it's at that point when the question arises that changes the lives of millions of people. Do you think nature would dedicate 4 coordinated mechanisms to a hormone that only serves to regulate digestion? Do you think that evolutionarily over millions of years we've kept such a hormone? Something so incredibly intelligent, so remarkably precise, and so multifunctional, just to process food? No, that is simply impossible. In a complex body like ours, a sophisticated molecule like that isn't just a simple digestive molecule. It serves a much greater purpose. A molecule like that has to be a molecule for something much bigger. But Haberner and Drucker in the 1980s still didn't know that. For them, GLP-1 was a hormone of the gut-pancreas axis, interesting for diabetics and promising for future drugs. Period. Nothing more. However, the true full scope of the GLP-1 hormone would still take 2 full additional decades to be finally revealed. And that major revelation would eventually come from a place that absolutely no one had expected. It would only come when scientific researchers began to systematically look for specific GLP-1 receptors in various tissues throughout the entire body. To put it more simply, those are the biological locks where the specific key fits perfectly. And when the researchers carefully mapped them out, they discovered these receptors in various places that seemed to make no logical sense at all. They were located in areas where a simple digestive hormone really had no business being. For instance, they found them deep within the brain, they found them inside the heart, and they even found them throughout the kidneys. And they discovered these specific receptors right there in the blood vessels. And there, right then and there at that pivotal moment, the story of GLP-1 stopped being just a story about diabetes and transformed into something else entirely different. But to understand why that discovery changed everything, I first need to tell you what was happening in parallel. Because while scientists were mapping those receptors, the pharmaceutical industry had already spent years looking at GLP-1 with different eyes. And what they made with it is the reason why you are watching this video. And here, if you like, I'll take a brief pause to look at it from another perspective. The story of GLP-1 had up until that point been the story of a digestive hormone, with some unexpectedly smart properties for treating diabetes, but nothing more. Although, of course, that alone was enough for the pharmaceutical industry to set its sights on it. In the late 1990s and early 2000s, several companies began developing drugs based on GLP-1. The first to cross the finish line was Amylin Pharmaceuticals with John N's exenatide. It was approved by the FDA in 2005. And then came other molecules increasingly stable with ever better design. Liraglutide in 2010, dulaglutide in 2014, and in 2017, semaglutide. Semaglutide is Ozempic. It's the same active ingredient. Ozempic is nothing more than the brand name from Novo Nordisk, the name they gave to semaglutide when they brought it to market. And you see, we could end the story here. The end. A hormone discovered in the 1980s that became a drug in the 2000s and was used to treat diabetes all over the world. A beautiful story of medicine and pharmacology, but one that's finished. However, as it remarkably turns out, the story did not simply end right there. At the same time that this was happening alongside this pharmaceutical development, there was an entirely separate group of researchers doing something that was seemingly mundane and tedious, something that rarely ever captured the public's attention or made any major headlines, and something that appeared to be much more like meticulous archival work than an exciting discovery. Those dedicated scientific researchers were meticulously constructing this incredibly detailed map. And let me explain exactly what that implies for our understanding. But before we get into the map itself, I need you to fully understand and be absolutely clear about one crucial thing, a small thing that changes everything. So what exactly is a hormone anyway? Essentially, a hormone is simply a biological messenger. It is a specific type of molecule produced by one of your internal organs, which is then released into the bloodstream, and subsequently travels to another distant organ, in order to give it a very specific set of instructions or a direct order. The pancreas produces insulin and sends it to your muscles. Store this sugar. The thyroid gland produces thyroxine and sends it to all your cells. Speed up the metabolism. The intestine produces GLP-1 and sends it to the pancreas. Produce insulin. Now these are chemical commands that travel along the highway of your bloodstream. That's all. But for that command to arrive, the target organ needs to have a receptor, a lock, where the key fits. And when a hormone travels through the blood, it doesn't act on just any cell in the body. It only interacts specifically with the cells that have its unique receptor, functioning much like a specialized lock. If a cell doesn't happen to have a receptor for that particular hormone, the hormone simply drifts right on past as if it didn't even exist. It is completely invisible and silent for that specific cell. That's why one of the first questions science asks when it discovers a new hormone is, where are its receptors? In which tissues of the body are there locks for this key? And making that map is slow work. You have to take tissues from every corner of the body, expose them to the hormone labeled with a fluorescent or radioactive molecule, and see where it sticks. Wherever it sticks, there is a receptor, and where it doesn't stick, there isn't one. When researchers began mapping GLP-1 throughout the 1990s and 2000s, they expected a fairly predictable result. Where should there be GLP-1 receptors? Well, it's very simple. In the places where we had already seen it act, in the pancreas, logically, where it regulated insulin, in the stomach, where it slowed down emptying, and maybe in some small area of the brain where it controlled appetite. And that was exactly what everyone had been anticipating. But the reality they eventually discovered was something entirely different altogether. The first thing that surprised them was what happened in the brain. They discovered that there weren't just GLP-1 receptors in the hypothalamus, which is the appetite region. There were receptors in deep areas of the brainstem, in regions that control the autonomic nervous system. There were receptors in the hippocampus, which is the memory region. There were receptors in the cerebral cortex, where conscious thought takes place. There were receptors in the ventral tegmental area, which is a deep region of the brain that regulates motivation and pleasure. And the question they asked themselves was, what is a digestive hormone doing talking to the region of the brain that regulates pleasure? And the second thing was the heart. There were GLP-1 receptors in the myocardium, which is the muscle of the heart. There were receptors in the nodes that regulate the heartbeat. There were receptors in the coronary arteries, which supply blood to the heart itself. And again, another question, what is a digestive hormone doing talking directly to the heart muscle? And the third thing was the kidney. Receptors in the nephrons, which are the functional units of the kidney. Receptors in the renal blood vessels. And now, what is a digestive hormone doing talking to the kidneys? And the fourth thing, perhaps the strangest, was the blood vessels in general. They found receptors in the endothelium, which is the inner layer that lines all the arteries and veins in the body. That thin layer of cells that is in direct contact with the blood. That's where they found receptors. In other words, GLP-1 could speak directly to the walls of your arteries. What is a digestive hormone doing talking to your arteries? Pause the video for a moment. Stop listening to me and think about all this information I'm giving you before you come back. Try to take it all in. A hormone that your intestine produces when you eat. Turns out it has locks installed in your brain, in your heart, in your kidneys, and in your arteries. It's not just one. It's 4 vital organs. And they're not just any 4 organs. They are the 4 organs that deteriorate the most with aging. They are the 4 organs that most often fail in elderly people. And they are the 4 organs where chronic diseases that kill humanity are concentrated. Dementia, heart attack, stroke, and kidney failure. Is it just a coincidence? No, it's not a coincidence. Biology doesn't work that way. When a system has locks so widely spread throughout the body, in such strategic organs, that can only mean one thing. That system has a much broader role than we thought. It is actually much, much deeper. And above all else, it is significantly older than anything else we have seen. But before we go on, let me explain exactly what a receptor is, because I've been using that word this whole time, and it's important that you understand it too. Think about it. In a cell, any cell in your body, that cell is surrounded by a membrane, a kind of ultra-thin skin that separates it from the outside. And that membrane isn't smooth. It's full of tiny proteins embedded in it that stick outwards. Each of those proteins is like an antenna or a lock that's waiting to receive a specific signal. And when a hormone like GLP-1 travels through the blood and encounters a cell that has its receptor on the membrane, the hormone attaches, fitting into the lock. And at that moment, a chain of chemical reactions is triggered inside the cell. The cell receives the message and acts. What message does it receive? Well, that depends on the cell. If it's a pancreatic cell, the message will be to produce insulin. If it's a heart muscle cell, the message will be something else. And if it's an endothelial cell, it will be something different again. The same key, it turns out, opens different doors depending on what's behind each door. But every single one of those different doors will actually respond and react to that very same key. And that is exactly what we are referring to when we say that GLP-1 has specific receptors located within the brain, in the vital heart, in the complex kidneys, and throughout the various arteries. It means that GLP-1 has the ability to send commands to those organs. It means that when you eat and your intestine releases GLP-1 into the blood, that hormone isn't just talking to your pancreas. At the same time, it's talking to your brain, your heart, your kidneys, and your arteries. And now, the big question is, what is it telling them? What command is it giving them? And that question, yes, that specific question, is what has changed medicine in the last decade. Because when researchers began to study what GLP-1 does in each of those organs, what they found was absolutely astonishing. One of the most striking observations came from the heart, because it turned out that diabetic patients who took GLP-1 drugs not only controlled their blood sugar better, it turns out they had fewer heart attacks, fewer strokes, and lower mortality. And that, in cardiology, is news you don't see every day. In fact, it hadn't been seen in decades. But before we get to the heart, where we're going to see some overwhelming data, I first have to take you to the organ that probably concerns you the most. And if it doesn't quite worry you just yet, I can absolutely assure you that it deeply worries your parents, your uncles and aunts, all of your in-laws, and perhaps it even concerns your partner as well. And maybe, even if you don't say it out loud, it worries you too. The brain. There is something that medicine has known for many decades now, and yet it is hardly ever mentioned in the media. It is an epidemiological observation so solid, so often repeated, and so well studied over time, that no one even questions it anymore. People with diabetes face twice the risk of developing Alzheimer's disease later in life. Read that again. Listen to it again. Yes, twice as much. No, not just a little more. Twice as much? And this isn't a weak correlation that showed up in a single isolated study. This has been observed in cohorts of hundreds of thousands of people in different countries with different methodologies and over decades. It's one of the most robust findings in modern epidemiology, and yet I'm the one telling you this here, and it's probably the first time you've heard it. And yes, I completely understand you. Go ahead, ask me the question. Ask me, why do diabetics have twice the risk of developing Alzheimer's? The explanation that has been developed over the last 20 years is so important that it even has its own name. There are serious scientists, neuroscientists, endocrinologists who call Alzheimer's type 3 diabetes. And it's not a metaphor. They literally call it that. When you study the brain of a person with Alzheimer's, you find something strange. It turns out that the neurons, especially in the hippocampus and cortex, lose the ability to properly use glucose. They develop insulin resistance just like the muscles and liver do in a diabetic. And here I need you to pause for a moment to consider what this means. When a muscle develops insulin resistance, the muscle suffers, yes. But the body has alternatives. It can burn fat, it can redistribute resources, and the muscle adapts. Not well, but it adapts. But the brain doesn't have that flexibility. The brain is the most demanding organ in the body. It consumes 20% of all your energy, even though it only accounts for 2% of your weight. And unlike muscle, it depends on glucose in an almost exclusive way. It has no reserves of its own. It can't burn fat directly. It needs glucose to arrive, enter, and be burned continuously without stopping. When neurons begin to develop insulin resistance, they gradually lose their essential ability to allow glucose to enter the cell. And without entry, there is no energy. And without this essential energy, the individual neuron first begins to slow down, then it gradually deteriorates, and finally, it dies. In other words, the brain of a patient suffering from Alzheimer's is, from a metabolic standpoint, a severely starving brain. It is completely surrounded by plenty of glucose in the bloodstream, but it simply can't get it in, and it can't use it effectively. And therefore, as a direct consequence, it can't nourish its own vital neurons anymore, and neurons without glucose die. So this completely changes the way we see the disease. For decades, Alzheimer's was explained as a problem of plaques. These are the well-known beta-amyloid plaques, a type of abnormally misfolded protein that accumulates between neurons and eventually suffocates them. And billions of dollars have been spent developing drugs to effectively target and eliminate those plaques. And the results so far, honestly, have been disappointing. While it is true that certain medications do manage to successfully diminish these amyloid plaques, even so, the clinical condition of patients often fails to show any significant improvement. And this observation has led many researchers to suspect that the plaques themselves are not actually the primary underlying cause of the disease. They suspect that they are only a consequence. They are a sign that something deeper has gone wrong beforehand. And that deeper issue, according to the type 3 diabetes theory, is the loss of the brain's ability to use glucose, the loss of sensitivity to insulin in the brain. And if that theory is correct, then anything that improves the brain's sensitivity to insulin should have beneficial effects on Alzheimer's. And here comes the connection. What does GLP-1 do? Let me remind you, GLP-1 is the hormone that tells the pancreas when to release insulin, improves the tissue's sensitivity to that insulin, and reduces inflammation. And we've also seen that it has receptors directly in the brain, in the hippocampus, which is the memory region, and which is also precisely the region that first deteriorates in someone with Alzheimer's. What happens if GLP-1 is talking to the hippocampus? What if it's been doing this for years in each of us? Every single time we eat, helping the brain stay healthy and function well. Is it possible that the gradual decline of that vital signal with aging is a key part of the problem? And if you take a look at this, these are not merely questions that I'm asking. They are the very questions currently being actively debated and discussed on the table at the world's most significant and prestigious scientific laboratories. Furthermore, there is already a substantial amount of supporting data available from various animal models. The effects of GLP-1 on the brain are truly impressive. When you give a GLP-1 agonist, a drug like Ozempic, to a genetically modified mouse designed to develop Alzheimer's, several things happen. Beta amyloid plaques are reduced, neuroinflammation decreases, and most notably, the neurons in the hippocampus end up having a longer lifespan. And what's even more important, the mouse also functions better, performs better in mazes, and remembers better what it learned the day before. And this has been repeated in dozens of studies in different laboratories around the world, with different animal models, and with various drugs from the GLP one family. The preclinical evidence is among the strongest that exists in Alzheimer's research. But mice are not people, and without a doubt, that's something I need to make clear to you. A great many drugs that worked spectacularly in mice later failed in humans. They did nothing. The history of medicine is full of animal promises that later were not fulfilled in people, and that is precisely why what has been happening recently is so incredibly important, because for some years now there have been clinical trials conducted in humans involving real people living with the realities of Alzheimer's disease. This research represents a significant step forward, and I'm going to tell you about two of them, the most important ones that have been done in this field to date. They're called EVOKE and EVOKE Plus. They were conducted by Novo Nordisk, the same Danish company that makes Ozempic, and they were, without exaggeration, the most anticipated clinical trials in neurology in recent years. EVOKE and EVOKE Plus are phase 3 trials, which is the most advanced and rigorous phase of clinical trials. Before a drug can officially be used for a new disease, it has to pass a successful phase 3 trial. And these trials recruited 3,808 patients, almost 4,000 people with early-stage Alzheimer's. Patients who had just been diagnosed with the disease or who were in the earlier stage known as mild cognitive impairment. Half received oral semaglutide, which is the same molecule as Ozempic but in pill form, and the other half received a placebo. And for 2 years, they were monitored with cognitive tests, blood markers, neuroimaging, and even, for a subgroup of patients, analysis of cerebrospinal fluid, that is, the fluid that directly bathes the brain and spinal cord. And what they were really asking was, does semaglutide slow the progression of Alzheimer's? Do patients who take it lose their memory more slowly than those who take a placebo? Do their brains atrophy less? Do their inflammatory markers improve? And on November 24th, 2025, Novo Nordisk announced the results. And now let me tell you exactly how it happened, because the story has two sides, and both are important. The first side, which made all the headlines, was a disappointment. Semaglutide did not manage to slow the clinical progression of Alzheimer's. Patients who took the drug lost memory at almost the same rate as those who took the placebo. Cognitively, functionally, in their day-to-day lives, there was no measurable improvement, and the industry reacted with sadness. Patient associations expressed their disappointment, and the media once again headlined that a promising drug had failed against Alzheimer's disease. And here we could end the story. Another drug that didn't reach its goal. Period. But the story had a second side, and that second side is the one almost no one has told you about. Because in a parallel sub-study within the same trials, the researchers collected cerebrospinal fluid from about 200 patients. They collected it at the beginning of the treatment and then again months later to compare. They wanted to see what was happening inside the brain at the molecular level, not just in cognitive scores. And what they found was absolutely spectacular and groundbreaking. Semaglutide had successfully reduced the concentration by up to 10% of the levels of the proteins that are most closely and significantly associated with Alzheimer's disease within the brain fluid. The tau protein in its most toxic forms, those called p-tau 181 and p-tau 217, had decreased. Neurogranin, which serves as a biological indicator of damage within the synapses, showed a measurable decrease. And most importantly, regarding the information I have been sharing with you, YKL-40, which represents one of the most specific biomarkers of neuroinflammation in the brain, had also decreased significantly. In other words, and this is very important for you to understand, the drug did not manage to make the patients remember better, but it did manage to change the biology of their brains in the right direction. Inflammation decreased, neurodegeneration decreased, and toxic proteins decreased. And a few weeks later, in April 2026, at the American Academy of Neurology Congress in Chicago, even more data came out. A mechanistic sub-study showed that semaglutide was directly modulating the activity of immune cells within the brain. It was specifically calming the immune cells in the brain, which I'll talk to you about in a moment. It was effectively reducing the inflammatory fever of the complex immune system within the brain. And now let me explain what all this means, because it has a very precise meaning, and it's neither that Ozempic cures Alzheimer's, nor that Ozempic is useless for anything related to the brain. What this means, what serious researchers are saying, is that semaglutide does indeed have effects in the human brain. This has been demonstrated without a doubt in the cerebrospinal fluid of real patients. What it is not able to do is reverse the damage once Alzheimer's disease is already clinically established. When there are already symptoms, when there are already dead neurons, reducing inflammation, 3 points. It does not restore lost memory. And this changes the question. The question is no longer, can Ozempic cure Alzheimer's? It becomes, can GLP-1 throughout your life and before any symptoms appear, keep your brain protected from the inflammatory cascade that ultimately leads to dementia? And that question is not answered by Evoke. That question would require a 20 or 30-year trial in healthy people with long-term cognitive follow-up. And that question will probably never be answered with the clarity of a clinical trial. But we do have clues, and the clues we have all point in the same direction. Epidemiological studies in patients with diabetes who have taken GLP-1 drugs for years show a significant reduction in the risk of developing dementia compared to diabetics who do not take them. And it's not causal proof, but it is a consistent signal repeated in different countries with different methodologies. And the signal is there. Dr. Ivan Koichov himself, a neuropsychiatrist at Imperial College London, explained it very well after the results of Evoke became known. And let me read it to you because his explanation is important. Koichov said, "This is a recurring issue in therapies for Alzheimer's. When the disease is already advanced, stopping the biochemical deterioration is not enough to restore the complex neural networks that have already been damaged." In other words, what he is saying, and it's important that you understand this well, is that we are arriving too late. When a person has already been diagnosed with Alzheimer's, even if you manage to reduce the inflammation in their brain, the neurons that have already been lost cannot be recovered. The connections that have already been broken cannot be rewoven. And the neural networks that have deteriorated are no longer there. And then he added a phrase that's worth remembering. He said, and I quote again, "The signal was always in the realm of prevention, not in that of treatment." In other words, the signal was always in the realm of prevention. And that, for you who are watching this video, is probably the most important lesson of the entire video, because you are not in the position of Evo's patient. You, at least I hope so, do not have Alzheimer's yet. You are in the position of someone who can still protect their brain. And the question you really need to ask yourself is not whether Ozempic will cure something for you in 20 years. The question is whether the GLP-1 signal in your body right now is working as it should. And if it isn't, what can you do about it? But before we get there, we still need to go back to a word that has come up several times recently, neuroinflammation, because it's probably the most important word you'll take away from here. And it's important that you know exactly what it means. Your brain has its own immune system. It's not the same one that defends the rest of the body. It's a separate, specialized system made up of cells called microglia. Microglia are like the police officers of the brain. They patrol, keep watch, clear out cellular debris, and attack viruses. Without microglia, the brain would become infected and fill up with waste in a matter of days. And the problem is that when microglia are overactivated for too long, they stop protecting and start causing harm. They become aggressive toward the neurons themselves, inflaming them, irritating them, and, pay attention, slowly killing them. Now, this specific condition is what we refer to as chronic neuroinflammation. And chronic neuroinflammation is, according to the most recent scientific theories, one of the primary drivers of brain aging, mild cognitive impairment, Alzheimer's disease, and many other various forms of dementia. So this naturally leads us to the next important question, which is, what causes microglia to become overactivated? Well, there are actually many contributing factors: a highly processed diet, clinical obesity, type 2 diabetes, chronic sleep deprivation, prolonged psychological stress, recurrent viral infections, and above all else, the natural process of aging. After the age of 50, microglia tend to become more reactive, less effective, and more inflammatory. And what does GLP-1 do? Well, let me tell you. Get ready to be surprised again. It calms the microglia, brings down its fever, and stops it from attacking. Hey, there's no longer an invader. And this has been seen repeatedly in animal models. When you administer a GLP-1 agonist, neuroinflammation markers go down, microglia return to their calm patrolling mode, and neurons are no longer in a combat zone. And this already has implications for a healthy, older person, because you don't need to have Alzheimer's to have neuroinflammation. You can have it at low levels in your 50s, higher in your 60s, even higher in your 70s, and it's part of normal aging. Reducing it and keeping it low is probably one of the best cognitive protection strategies that exist. And what we are discovering, in other words, is that GLP-1 is not just a hormone for diabetics, it's not just a drug for weight loss. It is one of the molecules that seems to have general protective effects on the aging brain. It is one of the molecules that nature designed to keep your brain functioning well for decades, and one of the molecules whose signaling in modern life might be diminished in many of us. And now try to keep this idea in mind for a moment, because when we get to the end of the video, you'll understand why activating it, whether pharmacologically or naturally, could be one of the most important decisions you make regarding how your brain will age. But you see, before we get there, the most important part is still ahead. Because if the data on the brain is promising, the data on the heart is no longer just promising. It's compelling. This is the data that changed cardiology in the last 10 years. And this is the data I'm going to show you now. And here, let me tell you, these data are of a different nature. What you've seen so far about the brain was promising, yes, solid as well, but nuanced by a trial that did not reach its primary endpoint and biomarkers that pointed in the right direction. But when it comes to the heart, that ambiguity disappears. The data on the heart is unequivocal. This is the data that, as I mentioned a moment ago, changed cardiology over the last 10 years and will shape the years to come. And this is the data that is currently leading cardiologists around the world to prescribe GLP-1 drugs to patients who don't even have diabetes. And here I'm going to tell you how it happened, because the story has a fascinating twist. Let's go back for a moment to the year 2008. The FDA, which is the agency that approves drugs in the United States, had experienced a scandal a few years earlier with a diabetes drug called rosiglitazone. It was a drug that effectively lowered blood sugar, but a meta-analysis published in the New England Journal of Medicine in 2007 showed something. Rosiglitazone increased the risk of heart attack. In other words, for years, millions of diabetics were prescribed a drug that controlled their blood sugar better, but was actually killing them with heart attacks. The FDA responded and, starting in 2008, issued a new regulation. Any diabetes drug that wanted to enter the market now had to prove, through a large clinical trial specifically designed for this purpose, that it did not increase cardiovascular risk. It didn't have to prove that it offered protection, only that it didn't cause harm. It was a defensive question, a question of safety. And so, when GLP-1 drugs entered the market, they had to undergo these cardiovascular trials. Liraglutide did so through a huge trial called LEADER, published in 2016 in the New England Journal of Medicine. Semaglutide did so through a trial called SUSTAIN-6, also published in 2016 in the same journal. These were trials designed to answer one question: do these drugs increase the risk of heart attack, stroke, or cardiovascular death? And remember, the question was defensive. No one expected the drugs to offer protection. They were only expected not to cause harm. But what happened was something else. And here, let me give you the specific data because it's important for you to understand the magnitude of what we're about to see. The leading trial, led by Danish cardiologist Stephen Marceau, recruited 9,340 diabetic patients with high cardiovascular risk. Half received liraglutide, the other half received a placebo, and all of them were followed for an average of 3 years and 8 months. And what was measured was the so-called MACE, which is a composite of 3: cardiovascular death, non-fatal heart attack, or non-fatal stroke. And this is the standard outcome in cardiology. 3.5 years later, they opened the data, and what they saw was that in the group that took placebo, 14.9% of the patients had suffered one of these 3 major cardiovascular events. In the group that took liraglutide, the percentage was 13%. And pause here, because at first glance that figure doesn't seem impressive. A difference of less than 2 percentage points. But think about what that means when you multiply it by all the high cardiovascular risk diabetics in the world. You're talking about hundreds of thousands of heart attacks, strokes, and deaths prevented every year. And in cardiology, that's huge. The technical term for that difference is called hazard ratio. And here I need to pause, because hazard ratio is a concept you'll hear a lot if you're interested in medicine, and it's worth having it clear. Imagine that the placebo group has a baseline risk of 100. That is, they have 100 arbitrary chances of having a heart attack. If the group with liraglutide has a risk of 87, we say that the hazard ratio is 0.87. Fewer than 100 out of every 100 people experience the event. And that, translated to large populations, means lives, many lives. In the LEADER trial, the hazard ratio was 0.87, 13% fewer major cardiovascular events. Statistically significant, rock solid. But there's more. Because when the results were broken down by components, it was seen that liraglutide not only reduced events overall, it reduced cardiovascular death by 22%. It reduced death from any cause by 15%, and those patients lived longer. And they lived longer not because they had lower blood sugar. They lived longer because they had fewer heart attacks, fewer strokes, and fewer cardiac events. And here comes the question that cardiologists asked themselves when they saw these data. The critical question: was this caused by the weight loss? Because it turns out that liraglutide caused weight loss. The patients in the LEADER trial lost an average of about 3 kilos. What if the cardiovascular protection simply came from that? What if it was an indirect effect of the weight loss and not of the drug itself? The researchers did the calculations, and what they discovered was that the protective effect of GLP-1 on the heart was too great to be explained solely by weight loss. Losing 3 kilos does not reduce cardiovascular mortality by 22%. Something else was going on, and that's when the results from SUSTAIN-6 came in. SUSTAIN-6 was the equivalent trial for semaglutide, that is, for Ozempic. 3,297 patients, 2 years and 1 month of follow-up. And here the results were, if anything, even clearer. Patients on semaglutide had 26% fewer major cardiovascular events than those who took placebo, with a hazard ratio of 0.74. This represents one of the most significant and largest reductions in risk ever documented with a pharmaceutical drug in the field of cardiology. And here I want to emphasize this because it's worth pausing to consider this figure: a 26% significant and measurable reduction in heart attacks, strokes, and cardiovascular death in patients diagnosed with high-risk diabetes, with the administration of only a single weekly injection. And what happened then? Once the results became public, everything changed in a very short time. Cardiology guidelines began to change. The American Heart Association, the European Society of Cardiology, and medical societies around the world started incorporating GLP-1s as a first-line recommendation for diabetics with cardiovascular risk. But not because of their effect on blood sugar, but because of their effect on the heart. And a few years later, SELECT arrived. It was published in 2023 in the New England Journal of Medicine. SELECT was the trial that closed the circle because SELECT was not conducted in diabetics. SELECT was done in obese people without diabetes, but with a history of cardiovascular disease. 17,604 patients. And in those specific clinical trials, a hazard ratio of 0.80 was successfully obtained. That is to say, there was a significant 20% reduction in major adverse cardiovascular events, specifically in people who were living without a diagnosis of diabetes. Think about it. That is correct in individuals living without diabetes. That was the specific trial that fundamentally transformed the entire paradigm. As of today, the medication known as semaglutide is no longer considered a drug intended only for one specific disease. Instead, semaglutide has now become a comprehensive drug that actively protects the entire cardiovascular system, and it provides these benefits regardless of the original clinical reason for which you might be taking it. After SELECT in March 2024, the FDA officially approved semaglutide for the indication of reducing cardiovascular risk in people with obesity and established cardiovascular disease. That is to say, right now, at the moment you are watching this video, there are cardiologists in hospitals in Madrid, Buenos Aires, and Mexico City prescribing Ozempic or Wegovy to patients who are not diabetic. And they are doing this because doctors now have clinical evidence that they are protecting their patients' hearts. But let's go back to the question, and it's the same one we've already asked ourselves before. What exactly is GLP-1 doing inside the heart and arteries? How does that 26% reduction in cardiovascular events translate into a biological mechanism? And now, as we embark on a quest to uncover these critical answers, we come to what is arguably one of the most remarkably fascinating and groundbreaking findings in recent cardiovascular biology. Because it turns out that GLP-1 functions simultaneously across multiple physiological levels within the body at once. First, the endothelium. And here I have to pause for a moment because endothelium is the key word in this part of the video, and it's important that you understand it perfectly. Your arteries and veins, all the blood vessels in your body, are not plastic pipes. On the inside, in direct contact with the blood, they have a layer of living cells, a very thin layer, just one cell thick, called the endothelium. If you were to spread out that layer completely, it would cover the surface of several tennis courts. In an adult, that layer weighs around 1 kilogram. In other words, it's practically an organ. And it's an organ that lines your entire vascular system. And that endothelium is not passive. It's not an inert lining. It's metabolically very active. It decides when the vessels dilate, it decides when they contract, and it plays a crucial role in regulating blood clotting, manages the process of local inflammation, and acts as a gatekeeper to determine which molecules are allowed to enter the vessels. The tissues, which one is it? No, I mean that in a very real and literal sense. It essentially acts as the primary director of the overall vascular health for your entire body. When that endothelium becomes inflamed, irritated, or dysfunctional, the entire vascular system starts to fail. The arteries become stiff and atheromatous plaques form more easily, blood pressure rises, and as a consequence, cardiovascular risks skyrocket. Endothelial dysfunction is, according to modern cardiology, one of the first changes that appear on the path toward heart attack and stroke. And what does GLP-1 do to the endothelium? It soothes it, reduces inflammation, improves its ability to produce nitric oxide, which is the molecule that tells blood vessels to relax and dilate, and reduces markers of oxidative stress, which are the molecules that damage endothelial cells over time. And this brings us to the second level, atheromatous plaques. Plaques are those accumulations of cholesterol, calcium, dead immune cells, and cellular debris that form within the walls of arteries. Over the years, and when a plaque becomes inflamed, it ruptures. And when a plaque ruptures, a clot forms. And when that clot blocks an artery, what has just occurred is what we call a heart attack. And if it blocks an artery in the heart, it's a heart attack, or a stroke if it blocks an artery in the brain. Well then, GLP-1 stabilizes plaques. It doesn't make them disappear, but it makes them less inflammatory and less likely to rupture. Studies using advanced vascular imaging have shown that in patients treated with GLP-1 agonists, plaques become more fibrous, more stable, and less dangerous. Third level, the heart muscle itself. The myocardium has GLP-1 receptors, as we've already seen, and when GLP-1 binds to those receptors, it improves the metabolic efficiency of the heart and allows it to use glucose better, which, remember, is its main fuel. But there's something more specific I want to tell you, because the heart can fail in two different ways. The first one is the one we all know. The muscle weakens, contracts with less force, and doesn't pump enough blood. And this is what we call heart failure with reduced ejection fraction. That is, the ejection fraction is simply the percentage of blood the heart expels with each beat. And if that percentage drops, the heart isn't doing its job properly. But there is a second form of failure, which for decades medicine failed to properly recognize. The heart muscle contracts with normal strength, expels the correct amount of blood, but then it can't relax. It stays stiff between beats, and that stiffness means the heart doesn't fill properly even though it pumps well. It's like a pump that pushes perfectly but can't fill up completely before the next cycle. And this subtype is called heart failure with preserved ejection fraction. And until very recently, it did not have an effective treatment. Conventional medicine knew it existed, diagnosed it, but had nothing specific to offer the patient. And that is exactly where the class of medications known as GLP-1 receptor agonists come into play. The STEP-HPPF clinical trial, which was officially published in the prestigious New England Journal of Medicine back in 2023, demonstrated that the drug semaglutide produced significant and meaningful clinical improvements for these specific patients, particularly regarding their overall quality of life and physical symptoms. Fewer symptoms, better exercise capacity, better quality of life. For the first time, there was something that worked. In that subtype and that analog, it turns out it's a molecule that your intestine naturally produces. Fourth level, blood pressure. Patients who take semaglutide see a modest but consistent reduction in their systolic blood pressure, on average between 3 and 5 millimeters of mercury, a number that seems small until you remember we're talking about millions of people. 3 millimeters of mercury in a population of 10 million people with hypertension means tens of thousands of strokes that don't happen each year. And why does blood pressure go down? Well, it's still not entirely clear, and it's worth mentioning because there are several hypotheses here. Less vascular inflammation, better endothelial function, reduced sympathetic tone, or probably all three at once. What is clear is that it happens, that it's consistent in the trials, and that it can't be explained solely by weight loss. In other words, GLP-1 is not doing something directly to the heart. Through the scale, it is doing something directly to the blood vessels. And here comes a fifth level, more subtle but important, systemic inflammation. High sensitivity CRP is a marker of general inflammation in the body. And patients who take GLP-1 agonists, on average, lower their high-sensitivity CRP levels. And that means GLP-1 is reducing the underlying inflammation throughout the entire body. That chronic silent inflammation, which many call inflammaging, meaning the inflammation associated with aging. And up to this point, I have just presented to you the 5 levels, 5 different mechanisms, and all of them go in the same direction. Protection of the cardiovascular system, cardiovascular. What a marathon. I'm really putting you through it. I hope you can bear with me. But now, zoom out, step back, at least in your imagination, and try to look at the whole picture. You see, I'm talking to you about a hormone that your gut releases every time you eat. A hormone that, from an evolutionary perspective, has been around since before mammals even existed. A hormone with receptors in your heart, your arteries, your brain, and your kidneys. A hormone that, when restored pharmacologically, reduces heart attacks. By 26%, it reduces strokes and lowers cardiac mortality in diabetic patients. It stabilizes your plaques, reduces inflammation in your endothelium, and lowers your blood pressure. It reduces the underlying inflammation across your whole body. Do you think a hormone like that is just a digestive hormone? Do you think so, after everything you've just heard in this video, that the main role of GLP-1 is to regulate when you eat and how much insulin you release? Seriously? No, that can't be. A hormone with these systemic effects is not just a digestive hormone. It's something else, something much more fundamental. It's probably what some researchers are already openly calling in the most recent papers. A geroprotective molecule, that is, a biological molecule that nature has specifically designed to safeguard and protect the organism from the effects of aging. And that's the idea you need to really understand, because it changes everything that follows. From here on, it changes how you understand Ozempic, it changes how you understand your own body, and it changes how you understand aging itself. Because if GLP-1 is a longevity molecule, then we have to ask ourselves the most uncomfortable question of all. Why do so many of us have this signal turned off? Why does modern life seem to have dampened precisely the molecule that protects us the most? And what can be done about it? I'm going to try to answer those questions coming up next. But first, I'm going to pause for a moment. Let's step out of the laboratories, the clinical trials, the hospitals. And I'm going to ask you a question that isn't strictly medical. It's a somewhat deeper question. And it's the question that I believe gives meaning to everything I've told you so far. Why does GLP-1 exist? And I don't mean why it was discovered, because we already know that. I mean, why has nature, over hundreds of millions of years of evolution, preserved this molecule so precise, so intelligent, with receptors in such strategic organs? What biological problem was GLP-1 solving when it first appeared? And the answer to these questions, once you understand them, I believe will once again change everything. Everything. And here, let's go back for a moment to the Gila monster. Do you remember him? It feels like ages ago that we talked about that lizard from the Arizona desert, the one that only eats twice a year. Wow, the hunger that guy must go through. This animal lives in an environment where food is scarce, unpredictable, and sporadic. And that's why it goes months without eating. And when it finds food, its body needs to do something very specific. It needs to switch in a matter of hours from a minimal survival mode to a mode where it makes the most of what it has just taken in. It needs to repair tissues. It needs to grow, if it still can. It needs to store reserves and activate all the body's costly processes that, however, had been shut down for months. And to do that, its body needs a signal, a clear, unmistakable signal that tells it, food has arrived. We are no longer in danger. We can invest energy in maintaining ourselves, in repairing ourselves, in taking care of ourselves. And that is the signal. In the lizard and in you, it's GLP-1. But let's see. Allow me to put what I'm telling you in a clearer way. GLP-1, in evolutionary terms, is not a digestive hormone. It's a signal of metabolic safety. It's the way your intestine notifies the rest of the body that there are resources, that the environment is favorable, and that it's possible to leave survival mode and enter into repair mode. And that's why it has receptors where it does, receptors in the heart. Because when there are resources, the cardiovascular system needs to be taken care of. The arteries become less inflamed, plaques stabilize, and blood pressure drops a bit. And the body says, now we can afford to keep the vascular system in good condition. Receptors in the brain, because when there are resources, the brain needs to be taken care of. The microglia calm down, inflammation decreases, and neurons are given permission to keep functioning well, and the body says, now we can afford to maintain memory, maintain thinking, and maintain cognition. Receptors in the kidneys, because when there are resources, filtration, cleansing, and homeostasis need to be taken care of, and so the body says, now we can afford to maintain the body's detoxification. Receptors in the endothelium, because when there are resources, the walls of the blood vessels need to be cared for, and here the body also says, now we can afford to maintain healthy tubes through which our blood circulates. And everything that GLP-1 does in each of these organs follows a unified logic. It's an evolutionary signal that you can invest in maintaining yourself. In short, that's a signal of longevity. Ancient biology, in its wisdom, connected a single digestive hormone to all the systems that deteriorate the most with aging. Because when there is food, you need to repair yourself, and when there is food, you need to age slowly. And here comes the uncomfortable part, the part that you should really understand because it changes how you think about your own body. What happens when that signal is weakened? What happens when, for whatever reason, the body stops properly receiving that message of you can invest in maintaining yourself? What happens is that the body stays in survival mode. Even if there is food around, and I'm going to explain it to you, when that signal is clearly present, all the organs that have GLP-1 receptors receive the message, you are safe, you can invest in maintaining yourself. And so, in the heart, the arteries become less inflamed. In the brain, the microglia remain calm, not attacking the neurons. And in the walls of the vessels and endothelium, repairs take place. Any plaques that may be present remain stable and do not become inflamed. The neurons are given permission to keep functioning well, and the kidneys stay young. But when that signal is turned off, all of that, it is reversed. The arteries throughout the body remain chronically inflamed, while the microglia in the brain become dangerously overactive and begin causing significant damage to surrounding tissues. Simultaneously, the delicate endothelium continues to deteriorate. The existing plaques become increasingly unstable and prone to rupture. The neurons gradually weaken over time, and the kidneys begin to age much faster than they naturally should. It is important to recognize that all of these complex biological processes are happening simultaneously across the entire system. In all the various organs, at the exact same time. Because it was that exact same signal, the very one that was actively protecting every single one of them. That same signal was turned off. And multiple systems that stop maintaining themselves. And here is the critical question of this video, the question you saw in the title, even if you didn't know it yet. The big question is, do we modern humans actually have that biological signal working properly today? And unfortunately, the honest answer is no. But I'm going to explain exactly why that is the case. Because here in our world today, there are at least 4 specific reasons why our modern life has significantly weakened the GLP-1 signal in most of us. Let's look at why this happens. And when you see them together, you'll understand much better why Ozempic has caused the earthquake it has caused. because Ozempic is not introducing something new into your body. Ozempic is restoring a signal that modern life has turned off in you. The first reason is processed food. GLP-1 is primarily secreted and released into the system, mainly in response to the consumption of actual whole foods, such as essential fiber, healthy fats, and nutritious proteins, specifically whole foods that pass through the small intestine and directly stimulate the L cells, which are the specialized intestinal endocrine cells that are responsible for the production of GLP-1. When you eat ultra-processed food that's full of refined sugars, white flours, additives, and emulsifiers, the L cells are activated much less. What you're doing is causing a spike in blood glucose, yes, but you're not triggering a good release of GLP-1. In other words, you eat, your blood sugar goes up, but you don't receive the full signal, the signal that real food has arrived and we can relax. And the body is left confused. It receives the carbohydrates, but it doesn't get the right message. Second reason, eating all day long. GLP-1, like many hormones, works in pulses. When you eat, it goes up, and after a few hours, it goes down. And then, when you eat again, it goes back up. And that rhythm of rises and falls is what keeps the receptors sensitive to the signal. This is because, like any biological communication system, it needs moments of silence so that when the message arrives, it can be heard clearly. However, modern life has eliminated those silences. We eat when we wake up, mid-morning, at lunch, mid-afternoon, at dinner, and we snack before going to bed. 5, 6, 7 times a day. Because there is constantly something moving through the small intestine, it essentially means that the critical GLP-1 signal no longer works in clean, distinct pulses as it should. It works like a constant background noise, and the receptors, when faced with a constant signal, lose sensitivity. They become deaf to it. This is exactly the same principle that makes you stop smelling your own perfume a few minutes after putting it on. Your nose loses sensitivity. The signal is still there, but you no longer register it. Third reason, the microbiome. The bacteria in your gut. They are enormously important for the production of GLP-1. And there is one particular bacterium, specifically called Akkermansia mucinifila, which is one of the major indirect producers of endogenous GLP-1. Akkermansia lives in the mucus layer that lines your intestine, and when it is healthy and abundant, it activates the L cells, which are the specialized cells in your intestinal wall that produce GLP-1. We saw them earlier. They are the ones that detect the presence of food and send the signal to the pancreas. Well, Akkermansia stimulates them directly, even without food being present. And there are also other bacteria that produce butyrate, a short-chain fatty acid, which has the same effect on those same cells. And there are also other bacteria that produce butyrate, which is a short-chain fatty acid that stimulates those same cells, L cells, so that they produce more GLP-1. These bacteria feed on fermentable fiber. Boiled and cooled potatoes, which I'll explain in more detail in a few minutes, plantains, oats, asparagus, it's no coincidence. It turns out that the foods which most effectively stimulate the production of endogenous GLP-1 are precisely the same ones that your grandmother always told you were good for your gut health. Modern life has been extremely harsh on these bacteria. Repeated antibiotics throughout life, a diet low in fermentable fiber, which is what these bacteria need to survive, chronic stress, environmental pollutants. And the result is that in adults from Western countries, the levels of Akkermansia are, when we look at the statistical averages, these levels are much lower than they were in our ancestors. And that directly means a significantly reduced amount of endogenous production of GLP-1. The fourth major contributing factor to consider is chronic stress. Cortisol, which is the stress hormone, interferes with many metabolic signals, and GLP-1 is no exception. When you live in a state of chronic stress, your body is constantly receiving a message that is the opposite of GLP-1's message. Cortisol says, we're in danger, don't invest in maintenance, get ready to escape. And GLP says, there are resources, we can invest in maintenance. And when those two signals clash, cortisol is the one that wins. It's an evolutionarily older, more urgent, and higher priority signal. And modern life, with its pace, its rush, its screens, its deaths, its demands. It keeps millions of people in a state of low-grade chronic stress. And this is a kind of stress that never fully turns off. It keeps your cortisol elevated for years, and without you realizing it, is silencing your GLP-1 signal every day. And now put it all together. Processed food that doesn't properly stimulate the L cells, eating all day, which saturates the receptors, an impoverished microbiome that produces less endogenous GLP-1, chronic stress that constantly shuts off the GLP-1 signal. Do you think your body today is producing GLP-1 at the level it evolutionarily should? Probably not. What this essentially signifies, when we look at it in very direct and practical terms, is that many of the critical systems that GLP-1 should be maintaining are being maintained significantly less than they truly ought to be. Your endothelium, your plaques, your microglia, your hippocampus, your kidneys, your underlying inflammation, all of these systems are operating with less protection than nature intended for you. And here, finally, we can fully formulate the thesis of this video. The thesis that gives meaning to everything I've told you. Aging, as we know it in modern life, is not a natural process in the purest sense of the word. It is, in part, an accelerated aging, due to the loss of protective signals that nature had given us and that our lifestyle has simply turned off. GLP-1 is one of its most important signals, perhaps the most important, and restoring it, whether pharmacologically with Ozempic or other drugs that act on the same mechanism, or endogenously through changes in how you live, is one of the most significant decisions you can make regarding how you are going to age. And if you want proof that this isn't just a fad, just look at what's happening in the world of money. Right now, there is an industrial war worth billions of dollars to control GLP-1. Eli Lilly, Pfizer, Roche, dozens of emerging biotech companies, Novo Nordisk, which manufactures Ozempic, was for several months the most valuable company in Europe. And not because someone had invented a weight loss pill, but because the market understood something that medicine will take years to officially acknowledge. GLP-1 is a longevity molecule, and whoever controls it will control a huge part of the future of human health. And this is what doctors are taking time to understand. Not because they're stupid, no, but because traditional medical training teaches you to treat diseases, not to maintain signals. And GLP-1 was not discovered as a longevity molecule, it was discovered as a molecule for diabetes. And it has taken us 40 years to truly understand what it actually was. But now, already by 2026, the most recent papers are starting to talk about GLP-1 in a completely different way. They're no longer just called anti-diabetics. They're no longer just called anorectics. More and more often, they're being referred to as gerotherapeutics, that is, drugs against aging. And that raises the practical question that everyone is asking right now. If GLP-1 is a longevity signal and my modern life has it switched off, what can I do about it? Should I inject myself with Ozempic? Or are there other ways to activate this signal? And the answer, as you're about to see, is that there are several ways to do it. And which one is right for you? It depends on who you are, it depends on the state of your body, and on what risks you have on the table. That's what we're going to talk about next. But let's start with the practical question. What do you do with all of this? I've told you that GLP-1 is a longevity signal. I've told you that modern life has turned it off. I've also told you that Ozempic restores that signal pharmacologically. And a moment ago, I left you with two questions. Do you inject yourself with Ozempic, or are there other ways to activate that signal? And before I answer you, let me tell you something personal because it's relevant. A little less than 3 months ago, I had open heart surgery. I had bacterial endocarditis, which is an infection that settles in the heart valves. And if it's not treated quickly, it kills you. They treated me well, I'm here, but the treatment that saved my life came at a cost. 40 days of antibiotics, both intravenous and oral. Powerful broad-spectrum antibiotics for 6 consecutive weeks. And that means something very specific for this conversation. My gut microbiome, that is the ecosystem of bacteria that had been with me my whole life, was wiped out. Akkermansia, butyrate producers, bifidobacteria, lactobacilli, everything. What had been helping me for decades to produce endogenous GLP-1 to maintain my intestinal barrier and to modulate my inflammation, all of that was gone in 40 days. And for a little less than 3 months now, I have been rebuilding my own body. What I'm about to explain to you now is not as a content creator, but as someone who had to study this topic in a hurry, because I had to apply it to myself. And that's why this video is important to me. And that's why what I'm about to tell you now, I'm going to explain with all the honesty I can. Because I've been applying it to myself every day since I wake up. And before we dive in, a quick recap. I just talked to you about the 4 saboteurs of GLP-1. Processed food, eating all day long, a damaged microbiome, and chronic stress. Well, for each of these saboteurs, there is a lever, a point of leverage from which you can push in the opposite direction. And the truly encouraging news is that most of them do not actually require you to make a trip to a pharmacy. What they truly and fundamentally require from you is a great deal of determination and consistency. Firstly ever, fermentable fiber. And this is the most important thing I'm going to tell you. If you take away only one thing from this video, let it be this. The bacteria that produce endogenous GLP-1, the butyrate producing ones, and those that keep the mucus layer healthy, where Akkermansia lives, all of them need a very specific fuel. And that fuel is called fermentable fiber. But pay close attention, because there's a common trap here. When people hear the word fiber, they often think of whole wheat bread, breakfast cereals, or snack bars with added fiber. But I want to be very clear that this is not the kind of fiber I am talking about. Fermentable fiber is something else. It's the fiber that your gut bacteria can break down and turn into beneficial fatty acids. It's the fiber that's mainly found in whole, unprocessed foods and in some very specific categories. You'll see which ones. Inulin and fructooligosaccharides are beneficial prebiotic fibers, which are naturally found in common vegetables like garlic, onions, leeks, fresh asparagus, and artichokes. Additionally, beta-glucans are healthy compounds, which are primarily found in wholesome, non-instant oats. And in barley, resistant starch, which is found in well-cooked legumes, green bananas, and, pay attention to this, in boiled potatoes. And then cooled afterwards for several hours in the fridge. And this phenomenon is called starch retrogradation. When you boil a potato, its starch becomes easily digestible for you. That's why a freshly made hot potato raises your blood sugar quickly. But if you let it cool for 12 hours, ideally overnight, part of that starch reorganizes into a new structure that your small intestine can no longer digest, so it passes whole, all the way to the colon, where your gut bacteria ferment and eat it to produce beneficial butyrate. This is one of the cheapest and most effective levers that exist. And here's an important detail. If you then reheat it gently in a pan with a bit of oil, for example, it still works. It only loses its effect if you overcook it at a very high temperature. In other words, you're not doomed to eat cold potatoes for the rest of your life. And this same principle also works with white rice, cooked and cooled, and with legumes. And think, for example, of salads with chickpeas, beans, or lentils. Then there are also pectins and polyphenols, which are found in apples, berries, pomegranates, and especially pomegranates, which contain compounds called elagitanins. When these reach the colon, they are transformed into molecules that specifically benefit Akkermansia. There are studies in humans that have been published showing this effect. Pomegranate, and I'm telling you seriously, it's not some hippie fad. It's one of the few natural things with a proven effect on Akkermansia. And what is the recommended amount for an adult audience? Well, ideally you should gradually work up to 30 or 40 grams of fiber per day, and mostly fermentable. Most people in Western countries don't even reach 15. That is, we're talking about doubling what normal people eat. And here's a warning. If your microbiome is depleted like mine is right now, you can't go from 15 grams to 40 overnight because it will make you feel bad. You'll feel bloated, gassy, and uncomfortable. You have to increase it, very slowly and gradually. Perhaps just 5 grams every single week, or even as little as 2. The most important thing for you to do is to let the beneficial bacteria you're feeding grow and multiply within the system first. And only after that should you start to slowly increase the total amount. Now we come to the second lever, polyphenols. I've mentioned pomegranate in passing, but it deserves its own space. Polyphenols are plant molecules that serve many functions, but the function we're interested in here is that they act as selective prebiotics. In other words, they specifically support the bacteria you want to have, especially Akkermansia. And what are they? The main sources: extra virgin olive oil, which is probably the most important in a Mediterranean diet. Green tea, which is especially rich in catechins, and catechins are the type of polyphenol that gives green tea its characteristic bitterness. And pay attention, they are also the ones with the strongest evidence for directly stimulating GLP-1. Endogenous, pure cocoa without any added sugar. That is, I mean high-quality dark chocolate. No, sorry, I definitely don't mean the typical supermarket milk chocolate. And red wine in very small amounts with some important caveats, because we know alcohol also harms the delicate microbiome. Additionally, you should include dark berries, red fruits, grapes with their skin, and pomegranate, as I already mentioned earlier, along with some healthy turmeric. Herbs and spices in general. The strategy is not to eat all of these things. The strategy is to make sure that every day you include several different categories of polyphenols on your plate. And diversity matters. Pay attention to that. And now let's move on to the third lever. Real fermented foods. And here, we need to make a distinction because there are products that say fermented or probiotic on the label and it's pure marketing. And there are real live fermented foods that are sold refrigerated, that have active cultures, and those are the ones you need to look for. Which ones are they? Authentic kefir, not the industrial imitations, and in particular, goat's milk kefir. And here's the practical reality, because you ask me about this a lot, in most supermarkets. What you're going to find is kefir made with pasteurized milk, or in the worst case, reconstituted from powdered milk. The one made from powdered milk basically doesn't provide any of the benefits we're looking for. So just rule that one out completely. And the one made from pasteurized milk is a different story. Pasteurization does eliminate some of the live microorganisms, yes, but if the manufacturer adds the cultures after the heat treatment, which is how good producers do it, the kefir is still functional. It's much better than nothing. And for most people who don't have access to artisanal kefir, it's a perfectly valid option. And how can you tell the difference? Read the label. Look for it to explicitly say live cultures added or fermented with cultures, active ones. If it doesn't say so, assume it doesn't have them. And one more note, because people often ask me, and because I myself drink kefir every day. From which animal? Well, look, my recommendation is goat kefir, if you can get it. Goat's milk is easier to digest than cow's milk, especially for adults and the elderly, because it has proteins that are gentler on the gut, and the fat is easier to process. But if you can only find cow's milk kefir, that's fine. But look for one made with A2 milk or of good quality. If you can't tolerate dairy, there's also water kefir, which is different, but it also benefits you. And the important thing in all cases is the same: live cultures, refrigerated, and with no added sugar. And of course, it should have a short ingredient list, because if you see sugar, syrup, flavorings, or stabilizers on the label, put it back on the shelf. In addition, natural yogurt with live cultures and no added sugar is also good for you, as well as raw, unpasteurized sauerkraut, kimchi, miso, or kombucha without added sugar. And here's an important comment. These fermented foods do not introduce Akkermansia directly into your gut, because Akkermansia is not present in these products. However, what they do is create a more favorable intestinal environment with greater bacterial diversity and resilience, in which Akkermansia will have a better chance of recolonizing if it arrives from somewhere else. And here is a study worth mentioning. Justin Sonnenberg from Stanford University published a study in 2021 in the journal Cell that compared two diets over 10 weeks, one high in fiber and the other high in fermented foods. The diet high in fermented foods increased the microbial diversity of the participants and reduced markers of systemic inflammation. And the fiber-rich diet also helped, but to a lesser extent. In this case, that is, the combination of both, fermentable fiber plus real fermented foods, is probably the most powerful thing you can do for your microbiome without medical intervention. The fourth key lever is the practice of intermittent fasting, but it must be done wisely. You see, as I have previously mentioned to you a little while ago in the video, that GLP-1 works in pulses, and eating all day long causes the system to lose sensitivity. The practical consequence is that leaving periods without eating allows the system to regain its sensitivity, and it gives the intestine time to regenerate the mucous layer where Akkermansia lives. So, what do I suggest to do it right? For most people, a nightly fast of 12 to 14 hours several days a week is enough to achieve the effect. And that means in practice that a nightly fast is enough to achieve the effect. Finishing dinner at 8 in the evening and having breakfast at 8 the next morning, that's 12 hours. And this was something that was commonly done in our grandparents' generation. They didn't call it intermittent fasting, it was simply normal life. And then for those who want to go further, you can do fasting windows of 16 or even 18 hours. But pay attention, this is important. Prolonged fasts are not for everyone, and if you are over 60 years old, if you have muscle loss, if you take medication, or if you are underweight, long fasts can do more harm than good. Keep this in mind, because in older people, preserving muscle mass is more important than any consideration of metabolic longevity. In my specific case right now, with a body in recovery after major surgery, I am not doing prolonged fasts. I am sticking to a simple 12-hour overnight fast, which is enough. But you should do whatever you feel works best for you. Just don't overdo it. Fifth lever, what you should reduce. Sometimes, what you stop doing is more important than what you start doing. There are three things that especially harm the GLP-1 signal and the health of the microbiome, and it's best to reduce them. 1. Artificial sweeteners, especially sucralose and aspartame. There are published human studies, and one particularly solid one from Eran Elinath's team in Israel, showing that artificial sweeteners alter the microbiome within weeks and worsen glucose tolerance. Zero-calorie carbonated drinks are not harmless. 2. Emulsifiers in ultra-processed foods. Polysorbate 80, carrageenan, carboxymethylcellulose. All of these are found in industrial ice creams, sauces, margarines, and in many so-called healthy supermarket products. All of them cause documented damage to the intestinal mucus layer. 3. Alcohol, especially when consumed habitually. Chronic alcohol use reduces microbial diversity. It damages the intestinal barrier and increases systemic inflammation, and I'm not talking about a glass of red wine with a meal, I'm talking about regular alcohol consumption. Sixth lever, and here I'm already entering the territory of supplementation, and I'm going to talk to you about it using my best judgment. Berberine is a plant alkaloid extracted from plants like barberry, and it has been used in Chinese medicine for more than 2,000 years. Barberry as a plant is not something you're going to find at your local grocery store, nor can you consume it in therapeutically useful amounts, but the alkaloid that gives it its properties, berberine, can be extracted and concentrated into capsules. And in this pharmaceutical form, over the last 20 years, Western research has shown that berberine activates an enzyme called AMPK, which is one of the main energy sensors in your cells. AMPK is activated when there is caloric restriction, when you fast, or when you exercise. And pharmaceutical berberine activates it without the need to go hungry. In other words, using it has certain consequences, similar to those of GLP-1, although through a better pathway. It improves insulin sensitivity, reduces inflammation, favorably modulates the microbiome, and benefits Akkermansia. And some studies compare it to metformin, that old diabetes drug, and claim it has similar effects. And the question that arises is berberine a natural substitute for Ozempic? Well, not exactly, because it works at a different point in the system and through a different pathway. But the end result, improving metabolic sensitivity and modulating the microbiome toward a more favorable profile, is indeed similar. And it's effective, inexpensive, and has a reasonable safety profile at standard doses, which are around 500 milligrams 2 or 3 times a day with meals, according to the most commonly used guidelines in human studies. In addition, there's pasteurized Akkermansia mucinifera. And this is something relatively new. Patrice Cani, a Belgian researcher who works at the University of Leuven, is one of the scientists who has contributed the most to understanding the role of the microbiome in metabolism, and he developed a pasteurized form of Akkermansia, that is, bacteria killed by controlled heat that retain their beneficial metabolic effects on the host. He published it in 2019 in the journal Nature Medicine, and since then, commercial versions have become available on the market. Does it work? Well, studies in humans are still limited, but they are promising. And in a situation like mine, where the microbiome has been wiped out by antibiotics, supplementation with pasteurized Akkermansia is one of the levers I'm using along with everything else. But a comment here. This isn't magic. It's just one more tool. And with this information, I've reached the end of the protocol. Allow me to recap once more. if what you want is to activate your endogenous GLP-1 system and protect what that signal does in your organs, the levers you have are these: fermentable fiber, real fermented polyphenols, simple overnight fasting, reducing artificial sweeteners, emulsifiers, and chronic alcohol use. If you want, smart supplementation with berberine or pasteurized Akkermansia. That's what's within your reach. No prescription, no doctor, and no Ozempic. Is it enough for everyone? No, there are people who need more. But for a metabolically reasonable person, without clinical obesity, without established diabetes, without very high cardiovascular risk, this set of levers, applied consistently and over months, restores the GLP-1 signal to functional levels. But what if you're not in this situation? What if you already have established type 2 diabetes, significant clinical obesity, or high cardiovascular risk? Or are you in a situation where endogenous activation doesn't arrive in time? Well, for those situations, there is Ozempic and other similar medications. And that's what I'm going to address next. With my best judgment, without demonizing it or idolizing it, just trying to understand it. And here the question at the end is very simple, as we asked before. Do you inject yourself with Ozempic or not? And the answer can only be, it depends on who you are. It's not a comfortable answer. And I understand that a lot of people want me to just say, thank you, yes, do it, or no, don't do it. But doing that after everything I've told you would be betraying the conversation we've had. You don't need me to tell you what you have to do. You need criteria. And as I told you at the beginning of the video, that's what I intended to offer you throughout all these minutes we've spent together. And the criteria, from my point of view, are these. If you have a confirmed diagnosis of established type 2 diabetes, if you are currently living with clinical obesity, along with all the serious health-related consequences that this chronic disease brings with it, and if your cardiologist has explicitly informed you that your overall cardiovascular risk is considered high or even very high, or perhaps if you have already suffered a heart attack or a stroke in the past, then these GLP-1 receptor agonist drugs are probably one of the most significant and transformative pharmacological advances we have seen in recent years. Important that medicine has seen in recent decades, and the evidence is overwhelming. They lower mortality, reduce heart attacks, protect the kidneys, and also help you lose weight and control blood sugar. In this situation, to speak badly of Ozempic out of ideology, trend, or general distrust toward the pharmaceutical industry would be irresponsible. Your doctor offers it to you because there is data, and data matters. If you are in an intermediate situation, without established diabetes, but with insulin resistance or significant overweight, or with metabolic risk factors, high blood pressure, or elevated inflammatory markers, then the question becomes more nuanced. There are reputable doctors who support the preventive use of GLP-1s in these profiles, and there are also reputable doctors who prefer to first exhaust endogenous levers. And you'll see both positions have their arguments. And here the criterion that should be applied is this. What have I already tried? Have I really changed the way I eat? Have I reintroduced meal rhythms into my diet? Have I taken care of my microbiome for months and not just weeks? If the answer is yes and the markers are still bad, talking to your doctor about a GLP-1 is reasonable. And if the answer is no, your body can probably still respond to natural levers if you give them to it. And if you are metabolically healthy, if your weight is reasonable, if your insulin sensitivity is good, if your inflammation is low, and if your heart is healthy, then you don't need Ozempic, you need something else. You need to keep your GLP-1 signal working well for the rest of your life. And that, as we've seen, this is done with fermentable fiber, with polyphenols, with real fermented foods, with nighttime fasting, with sleep, with less chronic stress, with less processed food, and by taking care of your microbiome. These are the essential strategic levers, and for you, in that specific situation, they are more than enough for your needs. These are the three general situations. Most people watching this video are probably in the first or the second situation. And that means that the decision of Ozempic or no Ozempic is not a binary one. It's a conversation you should have with your doctor, with the data in hand, with your medical history in front of you, and not based on an Instagram headline. And before we finish, here's a fact that will be useful for you to make your decision with perspective. The company that manufactures Ozempic, Novo Nordisk, has lost more than half its stock market value in less than 2 years. And not because the drug has stopped working, but because the competition is fierce. Eli Lilly already has its own molecule, Pfizer is in the race, and dozens of other companies are as well. And that means something very specific for you. Prices are going to drop. What is today an expensive and hard-to-access drug will become significantly more affordable in the coming years. And new options will appear with different mechanisms and different safety profiles. And if today Ozempic is not for you due to price or indication, don't close the door, because the landscape is going to change faster than most people imagine. But there is something that is valid for everyone. Regardless of whether you inject Ozempic, don't inject it, are considering it, or have completely ruled it out, there is one decision that is for you. The decision not to let your modern life keep shutting down. The longevity signal that nature placed in your body. That decision really is in your hands. And that decision is made every day, with every meal, every night you sleep well or poorly, every time you choose to walk for 20 minutes or not, every time you eat something real or choose a processed product, in every moment of silence. That you give your gut between meals, in every plate you fill with fermentable fiber or not. It's a decision that isn't made just once, just one time, it's made constantly over the years. And the effects are also cumulative over the years. That is GLP-1, that is longevity. That's what doctors are taking time to understand, and what you, after this video, already understand. And let me finally finish with something personal, because I'm not speaking to you from the outside. As I told you a while ago, a little less than 3 months ago, I came out of open heart surgery. And since then, every day, I myself apply what I've told you. And not simply because I'm a professional science communicator, but because I feel a personal obligation to do so. Because I have a body that is currently undergoing reconstruction. And because I know exactly how hard it is to lose a microbiome and how hard it is to rebuild it from the ground up. Because I deeply and personally understand, in my own physical body and flesh, exactly what it means for that longevity signal to be completely deactivated, and then to have to manually reactivate it once again. And I'll tell you this, it can be done. Slowly, with consistency, with patience, it can be done. I'm doing it. My test results are improving. My body is responding. And I, starting from zero, can do it. And if I can, it is important to realize that even those probably starting from much more than zero, they can certainly do it too. You see, GLP-1 is definitely not just a passing fad, and it is not merely a simple drug for losing weight. In reality, it is one of the very oldest, wisest, and most fundamental biological molecules that your own body naturally produces every single day. And understanding how it works, whether you decide to take Ozempic or not, whether you decide to change your life or not, it's about understanding one of the keys to how you age and one of the keys to how you live. What you've seen today is the first step of something. In the coming weeks, on this channel, we're going to start a new series called Biophysics of Summer, which will be 4 videos, each one as deep as this, but shorter, and each one with the same honesty, and each one also built on the same idea that understanding your body at its deepest biophysical level is the foundation of any sensible decision about your health. If this video has helped you, if it resonated with you, leave me a comment and tell me which part touched you the most. And if you know someone who could benefit from it, send it to them. Not for me, but for that person. And now I'll let you go. Take care of yourself. Take care of your signal. Take care of your microbiome. Take care of what you eat and how you eat it. Take care of your body, because it's the only thing you have to carry with you until the end. And as I always tell you, keep moving forward. Always forward. And I'll read your comments.